Welcome to IM1 11.4, video 2 of 2. There are 4 boxes for us to talk about, and the topic today is theorems about congruence transformations. There's only 2 theorems that we're going to talk about today, and let's dive into the first one right here. Theorem number 1, it's all about reflections in parallel lines theorem. Okay, so here is what it says. I'll try my best to explain it to you, and then I'll show it to you on GeoGebra, and then we'll do an example. I'll show it to you in pictures first. So let's say you have an object, right, or a figure in the plane. Like, so right now we have line segment AB. If I reflect line segment AB over line K, then obviously I would get A prime and B prime. And notice the reflection because we're going over the line K. So notice that B goes to B prime, obviously, and then A goes to A prime, okay? Then let's say I have another line, M, and K and M are parallel to each other, and we know they're parallel because they have the little red triangle thingies. And notice that they're perpendicular to each other down here. So therefore, if I reflect B over K, I would get B prime. And then if I reflect B prime over M, I would get B double prime. Okay, same thing works for A to A prime and then A double prime. But here is the really interesting part, all right? Whatever distance is between K and M, which we'll call it D, whatever distance that happens to be, then the distance from A to A prime is going to be twice this distance. And more importantly, I could just take this and translate it all the way over to here and end up with the same thing. So what this reflections and parallel lines theorem is saying is that if you do one reflection and then 2 reflections over parallel lines, it's the same as just translating the entire figure a distance of 2d, which happens to be the distance between the parallel lines. So that's what it's saying right down here. So if K and M are parallel lines, that's what we have here. K and M are parallel lines. And then a reflection in K followed by a reflection in M. So like we just talked about reflection, then reflection. It's the same thing as a translation. So if A double prime is the image of A, meaning that if A double prime is the point I ended up at and A is where I started, then line segment A to A double prime is going to be perpendicular to K and M. So that's what this is for. And number 2, A to A prime is twice the distance that the lines are separated. So let me show you an example of this in GeoGebra so you can kind of get a play around with it and you'll have an opportunity to play with it later. So let's say I have line segment DE, all right? And I can move line segment DE around anywhere I want. Notice it's being reflected over the first purple line, which we'll call F, right? No matter how I do it. Okay, and the other thing is that notice that the reflection I have, again, E double prime and D, so all the way over there. So everything is moving with 2 reflections, right? So the distance from B to F, if I move this around, is 3.37, and the distance from E to E prime is double that, 6.74. So no matter where I move this in the plane, you can see how those distances are related to each other. They are twice. So notice B to F is 4.44. And notice the distance from E to E prime is 8.88, exactly double that. And no matter how I move it, notice it stays the same, right? Still 8.88. The only thing that matters is the distance between the parallel lines. So I can move these things around and you can see that double reflection. So I could easily obtain the green segment just by doing a translation from E to E double prime. I don't have to do a double reflection. And that's what the Theorem 1 is trying to get you to understand. Okay, box number 2 is an example using the reflections in parallel lines theorem. So in the diagram, a reflection in line K maps GH to G prime H prime. So we're trying to map this guy right here to this guy right here. So the blue to the red, and that's going to be a reflection, which we can see because we have our distances from that reflection line. And then a reflection from, or in line M, from G prime H prime to G double prime H double prime. So then again, so we're doing from here to here. So we have 2 reflections. So we have 1 reflection and then we have 2 reflections. We also know a little bit of information. HB is worth 9, so I'm going to mark that up on here. Say from H to B is worth 9 units. So I'm going to mark that there. And we also know that DH prime, so D to H double prime, D to H double prime, this distance right here is worth 4. Okay? So that tells me that this distance right here is going to be 13. Because remember, this guy and this guy are going to be the same as this guy right here. Okay? So because we know it's a double the distance there. So let's do part A together. Okay? So part A is saying, can you name any segments that are congruent to GH? Well, yes, we can. So here's GH right here. So we know that G prime H prime is going to work. So G prime H prime, and that is a line segment, so I'll mark it as a line segment. Okay, and then I also know that this one over here, H double prime and G double prime. H double prime and G double prime. Those are going to be congruent. What about segments that are congruent to HB? So segment HB, let me get rid of these real quick for you. Okay, so segment HB is going from here to here. So that's worth 9 units that we're working with there. So we're trying to figure out, are there any others that are worth 9 units as well? HB is 9 units. That's the same thing as H prime to B right over here. So if we can say from H prime to B, that will also be worth 9 units. And then how about from G to A? So we want to go, I'll change colors for you again. So if I go from G to A, that distance right there, that's going to be the same thing as G prime to C right there. So we'll go G prime to A. Oh, sorry, this should be an A. Excuse me. This is an A. This distance is what I meant to say. G prime to A. There we go. So there's everything you know for part A. Let's do B together, okay? So part B is asking, does AC equal BD? So let me get rid of this and this and this and this. We can talk about it. So we'll do this in pink for you. Does A to C, so here's A to C right there, does that equal B to D? Well, the answer is yes, it does, right? And then explain why it does. And the answer is yes, because we know that G to G double prime is equal to H to H double prime. So, H to H double prime. So, therefore, we also know that the distance between here and here, between two parallel lines from our last unit, is going to be preserved in the same. So, therefore, we can say that this is basically a rectangle, and from A to C, which is the lower one, is going to be the lower half of the rectangle, and from B to D is going to be the upper half of the rectangle. So the answer is yes, we can definitely say that. And then part C, what is the length from G all the way to G double prime? Okay, so we want to go from here all the way to here. Well, that's going to be the same from here all the way to here. And we already figured out that this was 9, this was 4, and this was 13. So this is going to be a grand total of 9 plus 13 plus 4. So 9 plus 13 plus 4 is equal to 26. The other way you could think about that is it's just going to be 2 times 9 plus 4. So we take this segment and this segment, that's our 9 plus 4, and we double it to get our 26. So however you want to think about it, that's the way to do it. So that will definitely show up in your skill checks. Okay, box number 3 is theorem number 2. Remember, there are 2 theorems in this little video here. And let me walk you through the reflections one, and then we'll talk about it and show you the example with it. So, reflections and intersecting lines theorem. It says, if lines K and M intersect at point P. So let's get this straight here. So here's line M, here's line K, and they are intersecting at point P right down there. All right? And it says, if we have a reflection in K followed by a reflection in M, so let's start with this line segment AB. If I reflected in line K, I would get A prime and B prime, which is pretty obvious to see. And then if I reflect A prime to B prime over line M, this way I would get B double prime and A double prime. That's pretty easy to follow. So this one goes there, and the reflection, this one goes there as a reflection. That's pretty easy, but here's the cool part. The cool part is you can obtain this to this simply by doing a single rotation around point B, and that rotation's angles are connected. They're connected in such a way that whatever this is, if you call this X, then this is going to be double it. Okay, that's the important part right there. So we can obtain a reflection and then another reflection, 1, 2. We can obtain that by simply rotating this, whatever this angle is, and doubling it. All right, that's what it shows you. So let me show you that in GeoGebra real quick. So here's my other one, and you can play with this as well. So let's say I have the blue triangle, okay? And I can move the blue triangle, and notice it's reflected over the purple line, and you can see how things are moving around. That gives me the red triangle. And then notice how the red triangle is reflected over the green line. That's also moving around. So no matter how I move this thing around, you'll see that the reflections are happening. Here's the cool part. I could just obtain moving the blue triangle to the green triangle through a rotation, moving it exactly double the angle that's in between the purple and the black line, okay? So we can obtain this by doing a rotation, and that rotation is double the angle that's in between the purple and the black line. It's kind of hard to show on this because I'm rotating it the other way, but I did want to show you that you could obtain that rotation the same way we could reflect it. So no matter how we move things around, right? Even if I did that, the same thing happens if I move it over and double that angle in between the purple and the black line. So let's work with an example of that for box number 4. It's our last one. It says in the diagram, the figure of the fish is being reflected in line K, and then that's being reflected in line M. So I'm starting with the fish here. I'm going to reflect it over in line K, so notice the fish is kind of upside down. And then we're going to flip it over and reflect it on the side. So notice that the little dorsal fin has been switched around, right? And notice that the back tail fin is over here now. So I've got a reflection, then I have another reflection. And I know that the space between these two lines is worth 70 degrees. So the question is asking us, can we get a single transformation to get the blue fish over to the green fish? And the answer is yes, we could. Okay, when pink. We could just rotate this entire fish, this angle, and that angle is going to be 2 times whatever angle is in the middle. So the angle in the middle is worth 70. So if I rotate the blue fish around point P 140 degrees, that's to be a single transformation, because that's what it's asking me for, a single transformation, and it would map the blue fish onto the green fish, which is F to F double prime. So that's the relationship that we're looking for. Okay, that's the final video for this unit.